In the grand cosmic theater there are actors of unimaginable power and mystery. They are the universe's ghosts, the ultimate expression of gravity's dominion. We call them black holes. For centuries they were merely a chilling prediction, a mathematical curiosity, lurking in the equations of Albert Einstein's theory of general relativity. An idea so strange even Einstein himself was skeptical of their existence. They represent regions of space-time where gravity becomes so overwhelmingly powerful that the fabric of reality itself is warped beyond recognition, creating a prison from which nothing, not even light, the fastest thing in the universe, can escape. But what truly happens at the edge of this abyss, and what secrets lie hidden beyond it? How do these cosmic behemoths form, and how have we, on our tiny planet, managed to prove they are real? Today, we embark on an extraordinary journey, from the violent death of stars, to the mind-bending frontiers of modern physics, to unravel the enigma of black holes. To understand a black hole, we must first understand gravity not as a force, but as a curvature of space-time. Imagine a flat, stretched sheet. Any object with mass placed on it creates a dip. A planet like Earth creates a gentle curve. A dense neutron star creates a much steeper one. A black hole is what happens when mass is concentrated into such an incredibly small space that it punches a hole of seemingly infinite depth in the fabric of space-time. This extreme curvature dictates the universe's ultimate speed limit. To escape Earth's gravity, a rocket needs to travel at 11 kilometers per second. To escape a neutron star, you'd need to approach half the speed of light. But at a black hole's boundary, the escape velocity surpasses the speed of light itself. Since nothing can travel faster than light, the boundary becomes a one-way membrane. This is the event horizon, the point of no return. Black holes are not all created equal. The most common are stellar mass black holes, the ghostly remnants of colossal stars. When a star more than 20 times the mass of our sun exhausts its nuclear fuel, it can no longer support its own immense weight. The core collapses catastrophically, triggering a spectacular supernova explosion that blasts the star's outer layers into space. But the heart of the star continues to collapse inward, crushing itself into a point of unimaginable density, birthing a black hole a few times the mass of our sun. At the other end of the scale are the titans, supermassive black holes. These behemoths, weighing millions to billions of times the mass of our sun, reside at the heart of nearly every large galaxy, including our own Milky Way. Their origins are still a puzzle. Did they grow from stellar black holes, feasting on gas and stars for billions of years? Or did they form from the direct collapse of gargantuan clouds of gas in the early universe? Whatever their origin, they act as cosmic anchors, their immense gravity orchestrating the dance of stars and shaping the evolution of the galaxies they inhabit. Between these two extremes, astronomers hunt for the elusive missing link, intermediate mass black holes. And looking back to the dawn of time, some theories propose the existence of primordial black holes, forged not from stars, but from the turbulent, ultra-dense conditions of the Big Bang itself. These could range in mass from a small asteroid to thousands of suns, and some scientists even speculate they could be a candidate for the mysterious dark matter that holds our universe together. The event horizon marks the ultimate boundary, the limit of causal contact with the rest of the universe. Cross it, and no signal, no cry for help, no glimmer of light can ever reach the outside world. For a distant observer, the laws of relativity paint a strange picture. As an object falls toward the horizon, its light becomes increasingly stretched to longer wavelengths, a phenomenon called gravitational redshift. It would appear to slow down, getting dimmer and redder, seeming to freeze in time at the edge, fading over an eternity, but never quite crossing. But for the falling observer, the experience is dramatically different. For a sufficiently large, supermassive black hole, the crossing of the event horizon would be utterly unremarkable. You would sail past the point of no return without any immediate sign that your fate was sealed. However, for a smaller, stellar mass black hole, the tidal forces are extreme. The gravitational pull on your feet would be so much stronger than on your head that you would be stretched and torn apart in a process gruesomely nicknamed spaghettification. If black holes are truly black, how do we see them? The answer is, we don't. We see the chaos they create. Most observable black holes are surrounded by a swirling vortex of gas, dust, and shredded stars called an accretion disk. As this material spirals inward, friction and intense gravitational forces heat it to millions of degrees, causing it to blaze with radiation across the electromagnetic spectrum, from radio waves to powerful X-rays. These accretion disks can outshine all the stars in their host galaxy combined. In some cases, powerful magnetic fields channel some of this superheated material into colossal jets of plasma, which are then blasted away from the black hole's poles at nearly the speed of light. It is by observing this brilliant high-energy light and the dark silhouette or shadow that the black hole casts against it, that the Event Horizon Telescope was able to capture the first ever direct image of a black hole's event horizon. We can also detect them through their gravitational influence. We can watch stars orbiting a dark, empty point in space at incredible speeds, allowing us to calculate the mass of the unseen object. We can see how their immense gravity bends and magnifies the light of more distant galaxies behind them, a phenomenon known as gravitational lensing. And most profoundly, when two black holes spiral into each other and merge, they create violent storms in the fabric of space-time itself, gravitational waves, that we can now detect here on Earth. But what lies at the center? General relativity predicts that all the matter that falls into a black hole is crushed into a single point of infinite density and zero volume, a singularity. Here, our known laws of physics break down completely. This is where quantum mechanics must enter the stage. In the 1970s, Stephen Hawking showed that due to quantum effects at the horizon, black holes are not completely black. They should leak a faint thermal glow, now known as Hawking radiation, and very slowly, over unimaginable timescales, evaporate away. This leads to the famous black hole information paradox. If a black hole evaporates, what happens to the information of everything that fell inside? Quantum physics insists information can never be destroyed. This conflict has ignited a decades-long debate, pushing physicists to challenge the very nature of reality. Is the singularity real, or is it replaced by something even stranger? Proposals from string theory suggest a black hole is a fuzzball, a tangled mass of strings with a fuzzy surface instead of a sharp horizon. Other, more radical ideas propose a firewall of high energy at the horizon that would destroy anything crossing it. Another mind-bending concept, ER=EPR, speculates that the interior is a wormhole, connecting our universe to another. Right now, these are all tantalizing possibilities at the edge of human knowledge. The quest to understand what lies inside a black hole is nothing less than the search for a unified theory of everything. In the seemingly empty vacuum of space, the laws of quantum mechanics tell us that pairs of virtual particles, a particle and its antiparticle, are constantly popping into existence and then annihilating each other in a fleeting moment. In 1974, Stephen Hawking wondered what would happen if this occurred right at the edge of a black hole's event horizon. He realized it was possible for one particle to fall into the black hole, while its partner escapes into space. From an outsider's perspective, it looks as though the black hole itself has emitted a particle. This is Hawking radiation, and because the particle that fell in can be thought of as having negative energy, the black hole's total mass decreases. Stephen Hawking showed that black holes aren't perfectly black. Quantum effects cause them to emit radiation and slowly lose mass. For astrophysical black holes, this process is vanishingly slow. A black hole the mass of our sun would take 10 to the power of 67 years to evaporate, an amount of time vastly longer than the current age of the universe. But the fact that they evaporate at all raises deep questions. This is the heart of the famous information paradox. One of the core tenets of quantum mechanics is that information can never be truly destroyed. Yet a black hole seems to take in distinct information, the properties of the matter it consumes, and then evaporates away into perfectly random thermal radiation that contains no information at all. This is a fundamental clash between general relativity and quantum mechanics, and it's one of the biggest unsolved problems in physics. While these quantum effects play out on unimaginable timescales, on a galactic scale, black holes are powerful and immediate architects of cosmic structure. At the heart of most large galaxies, including our own Milky Way, lurks a supermassive black hole, millions or even billions of times the mass of our Sun. When these giants feed on surrounding gas and stars, they become what's known as an active galactic nucleus, or AGN. The energy released by this process is immense, launching powerful jets of plasma at near light speed and driving galactic-scale winds. This process, called feedback, heats up and blows away the cold gas clouds that would otherwise form new stars. Supermassive black holes regulate star formation and galaxy growth through this feedback from jets and winds. This isn't just a theory. Astronomers have observed a direct relationship between the mass of a galaxy's central black hole and the properties of its central bulge of stars. The link between a galaxy's central black hole and its bulge hints they co-evolve, making black holes central actors in cosmic history, shaping the very galaxies they inhabit. But what about the experience of a black hole up close? What would you experience falling into one? The answer depends entirely on your point of view. For a distant observer watching you, your descent would appear to slow down as you neared the event horizon. Your image would become redder and dimmer, a consequence of gravitational time dilation and redshift. They would see you seem to freeze at the edge, stretched and smeared across the horizon for eternity, never quite crossing. But from your perspective, you'd sail right across the event horizon without any immediate drama. The real danger is the tidal forces. For a smaller stellar mass black hole, the difference in gravitational pull between your head and your feet would be so extreme that you'd be stretched into a thin strand of atoms, a process gruesomely nicknamed spaghettification, long before you even reach the horizon. However, for a supermassive black hole, the tidal forces at the horizon are much gentler. You could cross the point of no return completely unharmed, only to be stretched and squeezed apart much later as you approach the central singularity. Many paradoxes come from comparing what different observers see. Once inside, all paths lead to the center. There, at the singularity, our current laws of physics break down. General relativity predicts a point of infinite density, which physicists know is a sign that the theory is incomplete. We still lack a complete quantum gravity theory describing the interior. To solve these mysteries, we need more data. Upcoming instruments like the space-based LISA observatory will detect gravitational waves from merging supermassive black holes across the cosmos, and the next-generation Event Horizon Telescope aims to create the first-ever movies of matter swirling around a black hole's shadow. These next-gen detectors and better EHT imaging will test new ideas and constrain models of gravity in its most extreme domain. Black holes sit at the crossroads of gravity, quantum mechanics, and astrophysics. They are the ultimate laboratories, pushing our understanding of space, time, and information to their absolute limits. Every new observation, every paradox uncovered, brings us one step closer to understanding the dark heart of the universe. If this journey to the edge of reality sparked your curiosity, subscribe for more deep dives into cosmic mysteries. And tell us in the comments, if you could ask a black hole one question, what would it be?